Okay, today we're going to talk a little bit about free body diagrams, and we're going to do some practice with it. So your activity at the very end is going to be to walk through kind of a simulator that helps you build free body diagrams, but you really do need to practice these on paper as well. So I'm going to walk through a few, and you can kind of pause the video in between to see if you can write out or draw out the free body diagrams. And so I've got some various situations that we're going to walk through. And so we're going to start with, let's just start with an easy one for right now. We're going to take this situation. We're going to see if we can do a box resting on a table. Okay, so that's going to be our first situation. Now, again, what I like to do is I like to have kind of an idea of what we're looking at. So here's our table, okay, and we're going to put a box, and we're just going to have that box resting on the table. So if we think about what's going on here, free body diagram, I always start them with a dot. The dot's going to represent the box. So there's my box, and now I'm going to look at all the forces acting on just the box. So we know that there's going to be weight acting on it, so we're going to expect there to be a force due to gravity acting on it, and that's going to be true of all objects. They all should have an F of G, that's their weight. And then the box doesn't move, so we know it's at stationary, so it's at equilibrium. So there's got to be a balance to that force, and that's coming from the table. So the table is pushing back on the box, and we refer to that as a normal force. So I'm going to draw an arrow up, label that as force normal, and I'm going to show that these two forces are equal to each other. And what we want to be able to do with this is build an equation from this. So I can write out now an equation. I only have one dimension to work with, so I'm going to say that the force normal is equal to the force of gravity. And so there's everything that I expect to get from a free body diagram. So that's our first situation. Let's look at another one, okay? And this one's going to be a little bit different. Here we've got now a car hitting the gas after a light turns green. So we're going to look at our situation here again. I'm going to start with drawing a little picture of a car. So here's my car, okay? And my car's sitting at this intersection, and now the light's going to turn green. So I know that, like, from a motion point of view, it's going to be picking up speed. So we know that our car is going to be accelerating. Now, when I look at this from a force point of view, I'm going to put my dot to represent my car. Okay, I know that the car is going to have some weight, so I'm going to put an F of G going down, and then I'm going to put a force normal going up because the ground is pushing back on it, and those should be the same size. So in other words, I know that the force normal is going to be equal to the force of gravity. Now, the important one for this is what's happening to the car in the X direction. So in the X direction, I know that the car's engine is going to apply a force. So we're going to draw in that force applied. Okay, so I've got an applied force. And then I know that the car is going to experience some friction with that road, and so that's going to be acting in the negative direction. Okay, and I'll label that as a friction force. Now you'll notice that I made this arrow smaller than this arrow, and I did that on intention because I know that to create that acceleration there has to be some kind of a net force, okay, because a mass times an acceleration is going to create a net force. And so that's where we're going to see the difference between these two. So our F net is going to be equal to the F applied minus our force of friction. So again, there's my free body diagram. There's the relationships that I get. I get two relationships because I have two different dimensions. So dimension 1, dimension 2. Okay? Let's look at another one, and we'll talk about something maybe on an angle. Okay? So here we've got a skateboarder that's rolling down a ramp. Okay, so I'm going to go ahead and we're going to start with my little bit of a picture. So here's my ramp. Okay, here's my skateboarder. Okay, and they're rolling down this ramp. So they are going to be going down the ramp. If I think about the motion that's acting with them, they should be getting faster each time. So I am experiencing some kind of acceleration, which means that I'm going to see a net force acting on them. Okay, here's my dot to represent my skateboarder on my ramp. And then we know that he's going to have weight acting down, so we're going to label an F of G going down. Now, the surface in this case is at an angle, so really the surface is pushing up on the skateboarder in this direction. So our normal force is going to be acting at an angle instead of acting straight down. Now, when we start to think about what's going on here, that normal force has to be balanced. And it's going to be balanced with this arrow right here, okay? And we're going to try to do this in a different color. So this is really the piece that's equal to that force normal. And it's part of the gravity that's acting on it. Now, the second component has to be the one that's going down. So again, we're making a little right triangle here. And this is going to be the piece of gravity that's pulling against the ramp, and this is going to be the piece of gravity that's pulling down the ramp. So in other words, those are the two pieces that make up gravity. It's like a triangle issue that we're seeing here. So in other words, the force of gravity is the hypotenuse, and then we get this force here, and we get this force here, and now the angle, okay, if we think about where that angle is, the angle is going to be relative to, see, this is the angle of the ramp. So the angle of the ramp, this will be the complement to that angle. So this is the angle that is the same as the ramp. So this is the cosine of theta times F of G. We sometimes call this the force perpendicular, so I refer to it sometimes as the force perpendicular. But then we also have this one, which is going to be the FG sine theta, and I sometimes call that one the force parallel because it acts parallel to the surface. So those are the two pieces that make up this part. Now really these two forces are not part of the free body diagram, so this and this are not in a free body diagram, and that's why I used a different color for them. The other force that we're probably going to have is we're probably going to experience a little bit of friction force, so we're going to put in a little arrow here that's going to represent our force of friction. So really there's three forces acting on our skateboarder: the force of friction, the force normal, and the force of gravity. Those are the three. But now we're going to resolve those into two equations. So like in this case, the force normal, we expect it to be the same size as part of the piece of gravity, so that's going to be equal to the FG cosine theta. And then the other one is that we're going to have that net force acting down. That's going to create that acceleration. So our F net is going to be the part of gravity that's pulling us down, the FG sine theta, minus our force of friction. So again, we're getting a free body diagram, and we're getting two relationships because we have two different dimensions. So this dimension, oops, excuse me, it's more like this dimension and this dimension. It's almost like we just tilted our paper, okay? And we looked at that force of gravity and split it up into its two pieces. Now part of that is because the force normal and the force of friction are always going to act as right angles to each other, okay? So that was a good situation. Let's do another situation here. Let's look at, say, a roller coaster being pulled up a hill, or tow hill, at a constant speed. So here we're going to have a roller coaster that we're going to pull up a tow hill. I'm going to draw this one. Let's see. Let's draw this one this way. So here's my tow hill, and here's my roller coaster. And it's being pulled up the hill, but this time the velocity is going to be constant. So remember, our dots are going to be equal in their space. So there's no acceleration. Okay, V is constant. Now if we look at this, again, there's probably going to be an angle associated with this, so we'll throw an angle in there. We're going to look at this in terms of our forces acting on our roller coaster. So it looks like I've got an F of G going down. I'm going to have my normal force that's going to act at an angle. And then I'm going to have some friction that's probably going to act a little bit this way. And then I have to have an applied force. So now I'm going to try to make my arrow the size that it needs to be to cancel everything out. So I'm going to make my applied force, okay, because that's the toe hill. So this is coming from the toe hill, this is coming from the surface, this is coming from gravity, and this is coming from the friction. So I'm looking at this in terms of trying to think, how big would these things be? So if I'm just going to put some light little lines in here to show that same right triangle again, I have a piece that would be acting this way and this way. So those two pieces have to cancel this one out. So if I think in terms of my equation, my applied force is going to have to be equal to my force of friction and the piece of gravity. So again, this angle right there is going to represent that. So that'll be an FG sine theta. So that has to be equal, because this is going to say that there is no net force. So net force is equal to 0, which means that the things going this way have to cancel the things going this way. So this is this way, these are this way, they have to be equal to each other so they can cancel out. Now in the other direction, it's the easy one. Our force normal is just going to be equal to that FG cosine theta. Okay, and so there we have it, free body diagram with the two equations that we get from it. Okay, let's look at one other one. Here I've got a wagon. Okay, we're going to pull a wagon with a handle that is at an angle with the ground at a constant speed. Okay, so let's slide this up here a little bit. Now, look at our wagon. So if we decide to do this one, let's see, here's my wagon. Okay, here's my handle at an angle. So here's us pulling our wagon. We know that the speed is the same, so it's constant. Okay, we're going to put our dot to represent the wagon. We're going to have our force of gravity acting down, so there's our force of gravity. We know that there's the handle's going to pull a little bit, so the handle's got to be the applied force. Okay, and then there should be a little bit of friction acting on this one. And there needs to be a force normal. Now the force normal is the interesting one. So again, if I start to think about what that applied force is doing, the applied force is pulling us this way and it's pulling us this way. So in other words, we're setting up that little bit of a right triangle here, and we're thinking in terms of the two pieces. So if this is my applied force, okay, this is the angle that the handle would make with the wagon. This would be then the F applied sine theta. So that means that we're lifting up on the wagon a little bit. And this would be our F applied cosine theta. That means we're trying to balance out the friction force. So really this piece here should be equal to this piece here. Okay, but now the downward piece has to be balanced by not just this upward piece, but also that force normal. So our force normal can change size because essentially the ground doesn't have to hold us up quite as much. So we'll go ahead and make our force normal a little bit smaller. So if you were tracking what I just said, it's the force of gravity would have to be pulling down, but that's going to be equal to that force normal plus what we're lifting up the wagon with, which is coming from that applied force. So it would be the applied force sine theta, so that little piece there. The ones that we're looking at in the other direction, so our other direction would be the friction force. And again, because this is moving with constant velocity, they should be equal to each other, should be equal to that other piece of the applied force. so that it cancels each other out. So again, the applied force is used in both because the applied force is not acting either vertically or horizontally, it's acting at an angle. So that's why we split that one up. But there's our free body diagram and our two equations. So there's a few examples that I walked through. If you would like to see more examples, I've got a whole stack of cards, and so you can have one of those in class to practice with. It's a good thing to do to make sure you're good at doing free body diagrams. It's going to help in doing all of the problem solving in this unit. So make sure you kind of follow through that, and I'm going to show you now the simulator that you're going to be using for your activity. All right, we finished up looking at free body diagrams and kind of doing some practice drawing. It's now time for you to do some practice, and we're going to go into the actual assignment. You can see I've got two different links here. This one is just, again, another little example that you can read through if you're still struggling with how to draw a free body diagram. But this is the one that you want for the simulation. So it's connected right back to the physics classroom. So you're going to click open this link, and you're going to see that it'll go into this launch interactive. And so we're going to do the launch of our interactive, and we're going to go ahead and do a big screen on this, and then we'll click start. Okay, they're going to have 12 different situations for you to create a free body diagram. So let's just kind of look at situation 1 and how it sets itself up. So you've got some various arrows that you're going to be able to put in. You've got your dot that you're going to work with, and they said it's a rightward force is applied to a dresser to accelerate it to the right across the bedroom floor, ignoring air resistance. So like the first arrow that we should have with everyone will always be that downward arrow. So let's go ahead and put a downward arrow, and we're going to call that the gravity arrow. So we know that we've got the F of G. So there's our force of gravity. Now we should have an up arrow as well, and that's going to be balanced by the normal. So we're going to throw that normal force in there. And then we're going to look at the dresser. Okay, we're going to apply a rightward force. So let's go ahead and apply that rightward force. And we want to have that be the applied force. And then we also need to have maybe a little bit of friction acting on us. So let's put a left arrow in there, and we'll give that one a friction arrow so you can see that we've got them. Now we need to change our sizes. So let's reduce the friction. Let's see, let's make that one smaller. Let's make that one bigger so that we can see that there's a definite difference in between so that they're going to create that acceleration. And then you just go ahead and you click on check, and it's going to give you an idea of whether you did it right or not. So it's a good way to get some feedback on them. I still suggest doing these on paper and having a few examples in your notes so that you know what you're going to do when you're working on problems. Okay? Good luck, and enjoy this activity. Just going back and remember the 12 situations that you're going to do, you are going to copy those onto a piece of paper, and those are going to get posted to the activity today. So just wanted to make sure you remember to do that as well. All right, have a good day.